Thank you very much. Can you hear me? My voice is not, I apologize, it's not in the best shape. So I'd like to convince you in this talk that Algebraic PRFS is a very useful tool for secure computation. Does it work? Great. So the starting point is the pseudorandom functions, just to make sure we are on the same page. So what is a pseudorandom function, right? So we consider we think of a collection of functions that if we pick a random function from this collection, then the PRF, the function's evaluations are indistinguishable from random function. Okay, it's a very standard definition. So algebraic PRFs have been introduced, at least in the way I am going to discuss here, by Ben Abbas, Gennaro, and Valls in 2011. And they have additionally two properties. So first of all, they operate over the range is essentially an abelian group. The very important property is that they support batch evaluations, batch PRF evaluations, given the secret PRF key. And in the, I'll call it the BGV paper. In that paper, they actually use this tool for verifiable computation, verifiable delegations of polynomial evaluations. So let's elaborate on these two last bullets. Okay, so this is very, very simple. Let's look at it very, very slowly. So here I use the same notations as the BGV paper. So if you want to look at the paper later, it will be easier for you. So there's this eval function, which is exactly the batch computation. What does it mean? It means that what is the okay? So here we have a product of a bunch of PRFs. And this function is parameterized by two, let's say, vectors. So the first vector is h, okay? So we have h and z. Yeah, I'm also not very good with the pointer. So let's start with the zi values. What are the zi values? These are the inputs to the PRF, to the batch PRF evaluations. So you see down there, for this talk, we only consider a special case where z is the vector of numbers, of integers between 0 and d, where d will be later the degree of the polynomial, of our polynomial. And the second parameter is the hi values. So here in this talk, we will only consider the exponent h. So hix is x to the I. Okay? So this eval computation essentially computes the product of L plus 1 PRF when evaluated to the sequential values from 0 to d, where each PRF evaluation is computed to the power of xi, x to the I. Okay? That's essentially as is the batch computation. And the interesting thing I'll show you in a second is that what they actually show is that you can compute a value very, very quickly. I mean, much faster than just computing each PRF individually. So I actually didn't want to talk about complete instantiations, but just I want to compare. I want to show you how to compare the protocols that I'll show you in a second, which probably work. So I'll just talk about two assumptions, two hardness assumptions. In the BGV paper, they consider these two assumptions, but they have a bunch of instantiations, not just the two concrete constructions that I will be talking here. Okay, so they have essentially, I will be considered two hardness assumptions here. This is the strong DDH, which is less standard assumption, which is also a dynamic assumption, right? There is some parameter D, and there is a bunch of elements, and we want to say that the distinguisher cannot distinguish between g to the xi, like g to the x, g to the x squared, and so on, from g to the x1, g to x2, and so on, where these values are picked at random. Okay? And the PRF below the assumption, that's essentially the PRF that we will be using for these algebraic properties. A DDH-based construction is then the famous, I guess most people already know that, the famous now-wrangled DDH construction. Okay? So forget for now about these constructions. I will present a general framework, but for the concrete analysis, I will be considering these two assumptions. So just to give you the intuition how if the eval function is computed. So basically, these two functions just imply or induce linear, so some formula, some algebraic formula. So if you think, essentially, we compute the element in the exponent, right? So for instance, before we had this function g to the k0, k1 to the x. So think of it, it's just if you add up the element in the exponent, you just get a formula, like even formula we learned in high school. So that takes a constant overhead to compute, assuming that exponentiation is done in constant time, right? The number of exponentiations is constant. And for now-wrangled, they actually used a formula, I think it goes back to the original paper of now-wrangled, where we could actually use log d exponentiations or overhead to evaluate that. Okay? So we have a bunch of d PRF evaluations where we instantiate the PRF under strong DDH assumption. We could do that, the eval computation in constant overhead. And where we instantiated with the now-wrangled function, we could actually do that in log d operations. Okay? Which is much faster than just computing d PRF evaluations and batching them together. Okay, so far so good? Good. Now, for some reason, I don't know why it doesn't work, the animation. Okay, so let's look at how they use this tool to actually compute verifiable computation of polynomial evaluation. So what is the setting? We have a client and we have a server. And the clients want to outsource, it has a large polynomial with degree d. D could be very large. And you want to upload the polynomial to the server. He wants to exploit the server's computation and storage services. And then you would like to send an input to the server. Okay, let's look that. Okay, look like that. Okay. So, so the client has this polynomial q of degree d. So we have d plus 1 coefficients. And this is what he outsourced to the server. So first of all, he sends the polynomial in clear. So that does not preserve any privacy. You'll see only correctness. And in addition, it computes the following. So first, it samples a random A from the corresponding field. We work in the exponent, remember. Next, for every coefficient, okay, it computes, you can view this as this one-time mac. So, for instance, for the first coefficient, we have q0. So it computes fk0 times g to the a q0, okay? And he's doing that for every coefficient using the same a, but every time use a different PRF evaluation. Okay, so that's what he's doing for the entire set of coefficients. And that's what he sends to the server. So we have the polynomial, and you can think of it as a set of one-time max. Okay, good. Next, we have, so this was the setup. Now we have evaluation phase. The client has some input, call it x. Okay. So he has some input x. He wants to receive back q of x. So the server computes q of x. That's not a problem, and sends it back. But now, of course, we don't trust this server, so we want to verify this computation. So in addition to computing q of x, so think of these elements, these elements, the additional elements that the client sends before in the setup phase. The server evaluates in the exponent this set of elements, okay? That's what he said. So think of, right, so we have that, Okay? So that stands for some sort of proof. It will be some sort of proof that the client uses to verify the computation. Okay. Now you see the box we just seen before. So, so in the verification phase, the client has Q of X, right? Q of X. So that's the polynomial evaluation, and he has some proof W. So what would he verify? He verifies that W equals to the sum of, right? So what is the Ri? So if you think of Fk 0, you can view it as a group element, right? We said that the range of the PRF is a group, is a abelian group. So you can think of it as G to the Ri, right? So essentially, it needs to verify this equality. Okay, is that clear? That's it. That's basically the verification, the verifiable computation that the client is doing. More importantly, why is it efficient? I mean, if the client has to actually carry out this all computation by itself, or just might have just evaluate the polynomial by itself. But by the property I just told you before, the eval function, so you see the punchline below, okay? This computation only requires sublinear time in the degree of the polynomial, okay? So the client actually doesn't need to work that hard in order to verify Q of X, okay? So that's basically how we use algebraic PRFs, the very, very basic construction. They had several more in the BGV paper. Good. So, so we already mentioned this doesn't have any privacy. And of course, it's a different setup than standard two-party computation, which I want to use this tool for. So the first functionality which I want to exploit this tool for, to compute, is Oblivious Polynomial evaluation. So let's define it in the two-party setting, right? We have two parties. The sender has it will be easier to call them a sender and a receiver. The sender has a polynomial, just like the client had before, with d+1 coefficients. And the receiver has an input x. And at the end of the protocol execution, the receiver needs to learn Q of X. Okay? That's the functionality. So let's tweak a little bit algebraic PRFs and change them in order to use this tool to realize this functionality. So before that, I just want to say that OP is a very, very, very important functionality where we use it has tons of applications. This is just a partial list, what you could actually do with it. So it's a very natural to try and compute it securely. Surprisingly, so far, the only two approaches, well, at least papers that you can actually find online, is either to use a paper by me and Yuda that requires some heavy machinery like cut and choose, or you could use a generic way of, for instance, what even presented using somewhat homomorphic and SIMD approach to compute OP. I'm sure you could actually design better protocols than what we already have, but while proving that the security, you'll see that you really need to use zero knowledge proofs, and it's not that simple to realize that. So basically what in this paper, what we're doing is that we realize this functionality in the exponent, and you could actually see why in the exponent, because everything, all the batch computation, everything was in the exponent before. And we do that with malicious security. And I'm going to explain it to you in abstract two phases. It's very, very simple. So in the first phase, the sender uses algebraic PRF to mask its polynomial and send this masked polynomial to the receiver. And in the second phase, they use what I call unmasking. So let me be more concrete, explain what I mean. So I am changing a little bit the way I'm using algebraic PRFs. Remember before we had this random A, and that's what gave us a property of one-time Mac. Now instead of using it for correctness, I want to use it for privacy. So I'm going to remove the A. I'm not going to use any A. Instead, I'll just, the sender computes the masking of its polynomial Q by multiplying component-wise each g to the qi, where qi is the ith coefficient, with fk of I, right? So you can view it as g to the ri, basically. So just you can think of it, you can view it as a special counter mode for groups, right? It's very similar to counter mode encryption scheme. And of course, the security, or at least the privacy, follows from the security of the PRF. Good. So this is the masking phase. Just one message. That's it. Next, we will do unmasking. So the receiver, given this masked polynomial, can evaluate it, right? Can compute the evaluation of Q plus R on some element X that he wants to evaluate. But of course, he has a wrong answer, right? So we need to correct that. So this correction is what I call unmasking. We want to remove this randomness. But you could probably now guess where I'm heading. So this unmasking essentially requires to compute this eval function that I defined before. And we already know how to do it in sublinear time in the degree of the polynomial. So there it is. That's it. That's the protocol. We have one message that only requires d plus 1 exponentiation. Remember that the sender knows the secret key, the secret PRF key. And we have an unmasking phase, which is sublinear indeed, right? And you could, if you go back, oh, sorry, wrong. Okay. If we go back to the protocol, so think of how easily this could be maliciously secure. I mean, all we need to take care of is that this unmasking phase would be secure against malicious adversaries. That's it. I mean, that's as simple as it. So that's that's the implementation for OPE, and it gets a much faster and simplified protocol than what we had so far, just by tweaking the use of algebraic PRFs. Okay, so let's not stop here. Let's see how we could actually use it to compute set intersections. So unfortunately, Benny is not here. He gave excellent tutorial on set intersection. So very simplified. This is the functionality that we have. Again, the sender and the receiver. They have two sets. The receiver wants to learn the intersection of these two sets. Good. And as Benny mentioned, this is a widely studied functionality. It also had a broad set of class of applications that we could actually use, and it has been studied a lot in the context of secure computation. And this is just a partial list. I don't even consider protocols in the random oracle because I'm not working in the random oracle. And two highlighted works. The former one by Yoretti and Liu from 2009. I'll reference to that work a bit later. And the later one is by myself and Kobi Nissim. So these two works are basically, if we don't consider the random oracle, so they gave the base asymptotic complexity. I'll say a few words more later. And in the plain model, we basically have two common approaches to evaluate set intersection. One of them was mentioned by Benny yesterday. This is the Oblivious Polynomial evaluation. which we will talk in a second. And you could actually already see how we could actually use the protocol that I just mentioned. And the other approach is Oblivious PRF evaluation. And I'm actually going to show you that Algebraic PRF is useful for both approaches. Good. So this is just a repeat on what Benny explained yesterday. How do we use polynomials to compute set intersection? So we build a polynomial where the set, or at least the sender, uses build a polynomial. Here T is a variable. So the set of elements in X are the roots, the set of roots of my polynomial. Okay, that's the polynomial that the sender constructs. And now let's try to, we could basically use the OPE constructions that we had before, that I just showed you. Essentially, the sender masks the polynomial, sends it to the receiver, and now the receiver evaluates this masked polynomial on the elements, on its own set of elements. Why? So here unmasking is slightly different. We don't really want to reveal the polynomial evaluation. We just want to make sure whether it equals the redundant part or not, because otherwise that would reveal information about the sender's polynomial, even if both parties are honest. So that's basically what we do in set intersection. And again, repeating on Benny's talk, this is a very naive approach. It gives a quadratic complexity because for each element in the set Y, the receiver has to evaluate the entire polynomial. It's this very naive approach. It works, but you're not happy about the complexity. No. That's why I said it one time Mac before. Okay. So very, very briefly, what we do, we use hash functions. This is, I will not go into the details, but essentially very standard way to do it. You just split the set of elements into bins, and now each bin implies or induces a polynomial, but the degree of this polynomial is much smaller than the entire degree, the entire set. And we essentially compare bin against, element to a polynomial that corresponds to the same bin. That's essentially what we do. This approach is not new. What's new here is that it's so much easier to actually do that because all this, we have algebraic structure. So remember, every time you want to design a zero-knowledge proof, the algebraic structure helps you a lot, right? It's very easy. So that's exactly what we have here also with the bins and the buckets and everything. It's so much easier to use this algebraic PRF. And let me just give you a hint. So Benny was talking about semi-honest security. When we switch to malicious, this turns out to be much more challenging. Basically, especially when we start using hash functions, because both parties have a lot of many ways they can actually cheat. The sender could use the wrong way of building the polynomials. It could actually, or it could enforce a zero polynomial, which is very bad. And the receiver could, for instance, in some of the implementations of these hash functions, like cuckoo hashing and balanced allocation hash functions, you actually have more than one hash function. You have either two or two with a stash. And you really need to make sure that the same element was evaluated with respect to each one of these hash functions. But these are all taken care with respect to it. It's very easy to actually prove that. So the overhead. So it doesn't give you much information. Just put some numbers here. I just want to stress. First of all, asymptotically, already it is better than so remember I told you my paper with Kobe. Essentially, it's the best paper. It's the most efficient paper that we have in the plane model, but it's so complicated. So if you remember, Benny showed a figure, F, H, and P. It was a protocol. It was very long. And this was already in the random oracle. I mean, removing the random oracle implies a much more complicated protocol. So I guess it's important to notice not just asymptotically it's much more efficient, but also it's simplification. I mean, I just explained to you in one slide, just 2 phases. That's it, basically. Okay, so I have 5 minutes. Let me just explain very quickly how we could use algebraic PRFs for the other approach, which seems less intuitive. I mean, before I was talking about polynomials, so everything goes out very, very nicely. But here I'm talking about Oblivious PRF. So what is Oblivious PRF? So again, we have a sender and a receiver, and the sender here has a PRF key, and the receiver has an input x, and the receiver wants to learn fk of x. That's basically the functionality. And how to use very quickly the algebraic PRFs to implement? How do we actually have a set intersection protocol? The sender picks a PRF key and evaluates the PRF on the elements in a set x, right? Fk x1, Fk x2, and so on. And we have a set of PRF elements, and he sends them to the receiver. And then they execute Oblivious PRF protocol for the elements of the receiver. Right. So basically, that's what. So the receiver has the set, evaluated set from the center, and the evaluated set from the Oblivious PRF evaluation. Now we can just compare. That's basically the approach, of course, and this is very simplified, but you can understand how it works. So actually, to make the proof works, we really need a stronger object, not just the Oblivious PRF, but something called committed Oblivious PRF. So what is committed Oblivious PRF? So basically, the receiver has, instead of one input, it has a set of inputs, right? And we want to make sure that the sender is using the same key, the same PRF key, for each one of the evaluations, right? So here this is described, the functionality is described in a non-adaptive form. Basically, so all the inputs are known in advance, but you can think of a variant of a functionality where the receiver picks adaptively the inputs to the PRF. Okay, good. So what I want to claim very quickly is that algebraic PRFs imply immediately committed Oblivious PRF, and why? So first of all, think of this eval function I started with. This is a product of PRF evaluations, right? So this eval function is PRF as well, right? I mean, if it's a product of PRF, you think of it as a PRF. So we will use this eval function as a PRF to implement our set intersection protocol. And essentially what I called the unmasking protocol before, this is what I call my PRF now. This is how I compute obliviously. That's it. Okay, sorry. Okay, so let me conclude. Just one. It's a very, very simple. Before it was very hard for us to actually build committed PRF. Algebraic PRFs give us a very efficient way to actually implement them, especially for an angle, which we didn't know how to do efficiently. And overhead is better, everything is better. Okay, just let's jump to the future research. This is just the take of the message I want you to take from this talk. I'm sure we could actually find more applications for algebraic PRFs. I just used for a concrete set of parameters, and so you can see that it just immediately gives me a set of protocols much more efficient and much more simplified. So we really need to maybe push this a little bit further. And just to conclude, there is a recent related work by Aloni, Shafi, and Vinod, which Aloni will be happy to tell you all about in the break, which is related to, I don't have time to explain. Okay, thank you, that's it.